First of all, the way a nonlinear autonomous system looks, you've had some practice with it by now. So this is nonlinear. So these are, the right-hand side are no longer simple combinations AX plus BY. Nonlinear and autonomous, there is no, these are functions of just of X and Y. There is no T on the right-hand side. Now remember, the way to get a geometric, most of today will be geometric. The way to get a geometric picture of that is first by constructing the velocity field, whose components are F, the functions F and G. So this is a velocity field. The velocity field which gives a picture of the system, and it has solutions. The solutions to the system, from the point of view of functions, they would look like pairs of functions, x of t, y of t. But from the point of view of geometry, they are, when you plot them as parametric equations, they are called trajectories of the field F, which simply means that they are curves everywhere having the right velocity. So a typical curve would look like, there's a trajectory, and we know it's a trajectory because at each point, the vector on it has, of course, the right direction, the tangent direction, but more than that, it has the right velocity. So here, for example, the point is traveling more slowly. Here it's traveling more rapidly because the velocity vector is bigger, longer. So this is a picture of a typical trajectory. The only other thing that I should mention are the critical points. If you've worked the problems for this week, the first couple of problems, you've already seen the significance of the critical points. Well, from Monday's lecture, you know, from the point of view of solutions, they are constant solutions. From the point of view of the field, they are where the field is zero. There is no velocity vector, in other words. The velocity vector is zero, and therefore a point being there has no reason to go anywhere else. Spelling it out, it's where the partial derivatives, not where the values of the functions on the right-hand side, which give the two components, the I and j components of the field, where they are zero. Okay, that's all I'll need by way of a recall today. I don't think I'll need anything else. The topic for today is another kind of behavior that you have not yet observed at the computer screen unless you've worked ahead. And that is, there are trajectories that sort of, go along to infinity or end up at a critical point. There are the critical points which just sit there all the time. But there's a third type of behavior that a trajectory can have, where it neither sits for all time nor goes off for all time. Instead, it repeats itself. Such a thing is called a closed trajectory. What does it look like? Well, it's a closed curve in the plane, which at every point, it's a trajectory, i.e. the arrows at each point, let's say it's traced in the clockwise direction, and I'll make the arrows, so the arrows will go, the arrows of the field will go like this. Here it's going slowly, here it's very slow, and here it picks up a little speed again, and so on. And now, for such a trajectory, what's happening? Well, it goes around in finite time and then repeats itself. It just goes round and round forever if you land on that trajectory. So it represents a system which returns to its original state periodically. It represents periodic behavior of the system. Now, we've seen one example of that. We've seen an example of that, a simple example where of this simple system, x prime equals y, y prime equals x, negative x. We can write down the solutions that directly, but if you want to do eigenvalues and eigenvectors, the matrix will look like this. The equation will be lambda squared plus 0 lambda plus 1 equals 0. So the eigenvectors will be plus or minus, eigenvalues will be plus or minus I. But in fact, and then from then on, you can work out in the usual way the eigenvectors, but complex eigenvectors and separate them into the real. But look, you can avoid all that just by writing down the solution. The solutions are sines and cosines. One basic solution will be x equals cosine t, in which case, what is y? Well, y is the derivative of that. So that will be minus sine t. Another basic solution will start with x equals sine t, in which case y will be cosine t, its derivative. Now, if you do that, what do these things look like? Well, either of these two basic solutions looks like a circle, not traced in the usual way, but in the opposite way. For example, this starts when t is equal to 0. It starts at the point 1, 0. Now, if the minus sign weren't there, this would be x equals cosine t, y equals sine t, which is the usual counterclockwise circle. But if I change y from sine t to negative sine t, it's going around the other way. So this circle is traced that way. And all the other circles, this is a family of circles, all of which, according to the values of C1 and C2, concentric, all of which go around clockwise. So those are closed trajectories. Those are the solutions. They're trajectories of the vector field. They're closed. They come bound right, and they repeat in finite time. Okay, now, these are no good. These are the kind I'm not interested in. These are commonplace. We're interested in good stuff today. And the good stuff we're interested in is limit cycles. A limit cycle is a closed trajectory with a couple of extra hypotheses. So it's a closed trajectory, just like those guys, but it has something they don't have, namely, it's king of the roost. They have to be isolated, no other guys nearby, and they also have to be stable. See, the problem is here that none of these stands out from any of the others. In other words, there must be isolated means no others nearby. That's just what goes wrong here. Arbitrarily close to each of these circles is yet another circle doing exactly the same thing. That means that in their sum, they're only of mild interest. What's much more interesting is to find a cycle where there's nothing nearby. Something, therefore, that looks like this. Okay, here's our pink guy. Let's make this one go counterclockwise. So here's a limit cycle, it seems to be. And now, what do nearby guys do? Well, they should approach it. So somebody here, like that, does this. Spirals and gets ever and ever closer to that thing. Now, it can never join it. It can never join it, because if it joined it at the joining point, I would have two solutions going through this point, and that's illegal. So all it can do is get arbitrarily close. On the computer screen, it will look as if it joins it, but of course it cannot. It cannot. It's just the resolution, the pixels, not enough pixels. The resolution isn't good enough. And the ones that start further away will take a longer to find their way to the limit cycle, and they'll always stay outside of the earlier guys, but they will get arbitrarily close too. How about inside? Inside, well, it starts somewhere, and it does the same thing. It starts here, and we'll try to join the limit cycle. That's what I mean by stability. Stability means that nearby guys, the guys that start somewhere else, eventually approach the limit cycle, regardless of whether they start from the outside or start from the inside. So that's stable. An unstable limit cycle, but I'm not calling it a limit cycle if it's unstable. I'm just calling it a closed trajectory. But let's draw one which is unstable. Okay, here's the way it will look if it's unstable. Guys which start nearby will be repelled, driven somewhere else. Or if they start here, they'll go away from the thing instead of going toward it. So this is unstable, and I don't call it a limit cycle. It's just a closed trajectory. Cycle, because it cycles round and round. Limit, because it's the limit of the nearby curves. The other case where it's unstable, it's not the limit. Of course, you could have a case also where the curves outside spiral in toward it, but the ones inside are repelled and do this. That would be called semi-stable, and you can make up all sorts of cases. And I think I, at one point, drew them in the notes, but I'm not going to. The only interesting one of permanent importance that people study are the actual limit cycles that are the stable closed trajectories. Notice, by the way, a closed trajectory is always a simple curve. Remember what that means from 1802. Simple means it doesn't cross itself. Why doesn't it cross itself? It can't cross itself because if it tried to, what's wrong with that point? At that point, which way does the vector field go? That way or that way? Why the interest in limit cycles? Well, because there are systems in nature in which just this type of behavior, they have a certain periodic motion, and if you disturb it, gradually it returns to its original periodic state. A simple example is breathing. Okay, now I made you all self-conscious. All of you are breathing. If you're here, you're breathing. At what rate are you breathing? Well, you're unaware of it, of course, except now. Now, if you're sitting here listening to a certain temperature, certain air circulation in the room, not thinking of anything, certainly not of the lecture, and the lecture is not unduly exciting, you'll breathe at a certain steady rate, which is a little different for every person, but that's your rate. Now, you can artificially change that. You could say, okay, now I'm going to breathe faster. And indeed you can, but as soon as you stop being aware of what you're doing, the levels of various hormones and carbon dioxide in your bloodstream and so on will return your breathing to the natural state, to its natural state. In other words, it's behaving, that system of your breathing, which is controlled by various chemicals and hormones in the body, is exhibiting exactly this type of behavior. It has a certain regular periodic motion as a system, and if disturbed, if artificially you set it out somewhere else, it will gradually return to its original state. Now, of course, yeah, but if I'm running, of course it'll be different. Sure, if you're running, you breathe faster, but that's because the parameters in the system, the A's and the B's in the equation, the f and the xy, the f of xy and g of xy, the parameters in those functions will be set at different levels. You'll have different hormones, different amount of carbon dioxide, and so on. Now, I'm not saying that breathing is modeled by a limit cycle. It's the sort of thing which one might look for a limit cycle. That's of course, a question for biologists. in general, any type of periodic behavior in nature, people try to see if there is some system of differential equations which governs it, in which perhaps there is a limit cycle, which contains a limit cycle. Well, what are the problems? In a sense, limit cycles are easy to lecture about because so little is known about them. At the end of the period, if I have time, I'll show you that the simplest possible question you could answer is totally, the answer to it is, the answer to it is totally unknown after 120 years of trying, steady trying. Okay, but let's first talk about what sorts of problems people address with limit cycles. First of all is the existence problem. If I give you a system, you know, the right-hand side is x squared plus 2y cubed minus 3xy, and the g is something similar. I say, okay, does this have limit cycles? Well, you know how to find its critical points. But how do you find out if it has limit cycles? The answer to that is nobody has any idea. So this problem is, in general, there are not much in the way of methods. Not much. Not much is known. There is one theorem that you'll find in the notes, a simple theorem called the Poincare-Bendixson theorem, which for about 60 or 70 years was about the only result known which enabled people to find limit cycles. Nowadays, the theorem is used relatively little because people try to find limit cycles by computer. Now, the difficulty is you have to know where to look for them. In other words, the computer screen shows that much, and you set the axes, and it doesn't show any limit cycles. That doesn't mean there aren't any. That means they're over there. Or it means there's a big one, like there, and you're looking in the middle of it and don't see it. So in general, people don't look for limit cycles unless the physical system, which gave rise to the set pair of differential equations, that physical system suggests that there is something repetitive going on, like breathing. And if it tells you that, then it often gives you approximate values of the parameters and of the variables, so you know where to look. So basically, this is done by computer search. By computer search, guided by the physical problem. Therefore, I can't say much more about it today. Instead, I'm going to focus my attention on non-existence. How can you be sure, when can you be sure that a system will not have any limit cycles? And there are two theorems. One, again, due to Bendixson. Bendixson was a Swedish mathematician who lived there in around 1900 or so. There's a criterion due to Bendixson, and that's the one and there's one involving critical points, and I'd like to describe both of them for you today. So first of all, Bendixson's criterion. It's very simply stated, and it has a marvelous proof, which I'm going to give you. Okay, so we have D as a region of the plane. And what Bendixson's criterion tells you to do is to take your vector field and calculate its divergence. So we are sent back into 1802, and this proof is going to be straight 1802. You'll enjoy it. Calculate the divergence. Now, I'm talking about the two-dimensional divergence. So remember, that is fx, the partial of f with respect to x, plus the partial of the j component, with respect to y. And assume that that's a continuous function. It always will be with us. practically all the examples I'll give you, f and g will be simple polynomials, so they're as smooth and continuous and nice behaved as you want. And now the assumption is, so you calculate that, and you assume, suppose in other words, that the divergence of f, well, let me write, I need more room too. So the hypothesis is that the divergence of f is not 0 in that region D. It's never 0. It's not 0 at any point of that region. The conclusion is that there are no limit cycles in the region. If it's not 0 in D, there are no limit cycles. In fact, what there aren't are not even any closed trajectories. You couldn't even have those bunch of concentric circles. So there are no closed trajectories in. Of what? Of the original system whose divergence you calculated. So there are no closed trajectories in D. For example, well, let me give you a simple example, just so that it'll put a little flesh on it. Let's see, what do I have? I prepared one. Example, x prime equals, so here's a simple nonlinear system, x cubed plus y cubed, and y prime equals 3x plus y cubed plus 2y. Does this system have limit cycles? Well, even to calculate its critical points would be a little task. But we can easily answer the question as to whether it has no limit cycles or not by Bendixson's criterion. Let's calculate the divergence. The divergence of the vector field, whose components are these two functions, is, well, 3x squared. It's the partial of the first guy with respect to x plus the partial of the second guy with respect to y, which is 3y squared plus 2. Now, can that be 0 anywhere in the xy plane? No, because it's the sum of these two squares. This much of it could be 0 only at the origin, but that plus 2 eliminates even that. This is always positive in the xy plane, in the entire xy plane. So here, my domain is the whole xy plane, and therefore the conclusion is that there are no closed trajectories in the xy plane anywhere. And we've done that with just a couple of lines of calculation and nothing further required. No computer search. In fact, no computer search could ever prove this. It would be impossible because, no matter where you look, there's always some other place to look. This is an example where mathematics, a couple of lines of mathematics dispose of the matter far more effectively than $1 million worth of calculation. Well, where does Bendixson's theorem come from? Aha, yes. Bendixson's theorem comes from 1802. And I'm giving it to you both to recall a little bit of 1802 to you, and because it's about the first example in the course that we've had of an indirect argument, and it's something, indirect arguments is something you have to slowly get used to. I'm going to give you an indirect argument, indirect proof. Remember what that is. You assume the contrary, and you show it leads to a contradiction. So what would assuming the contrary be? Contrary would be, I'll assume the divergence is not 0, but I'll suppose there is a closed trajectory. So suppose there is a closed trajectory. So suppose a closed trajectory exists. Okay, let's draw a picture of it. Well, okay. And let's say it goes around this way. So there's a closed trajectory for our system. Let's call the curve C, and I'm going to call the inside of it R, the way one often does in 18.02. D is all this region out here in which everything is taking place. So this is to exist in D. Now what I'm going to do is calculate a line integral around that curve. A line integral of this vector field. Now, there are two things you can calculate. One of the line integral, I'll put in a few of the vectors here. That one. The vectors, I know they're pointing this way because that's the direction in which the curve is being traversed in order to make it a trajectory. So those are a few of the typical vectors of the field. Now, so I'm going to calculate the line integral around that curve in the positive sense, not, in other words, in the direction of the salmon-colored arrow, but in the normal sense in which you calculate it using Green's theorem, for example. So the positive sense means the one which keeps the region, the inside, on your left, right? As you walk around like that, the region stays on your left. That's the positive sense. So that's the sense in which I'm integrating. And I'm going to use Green's theorem. But the integral that I'm going to calculate is not the work integral. I'm going to calculate instead the flux integral. The integral which represents the flux of F across C. Now, what is that integral? Well, at each point, you station a little ant, and the ant reports the flow rate across that point, the outward flow rate across that point, which is F dotted with the normal vector. I'll put in a few normal vectors just to remind you. The normal vectors look like the little unit vectors pointing perpendicularly outwards everywhere. So these are the ends. So F dotted with the unit normal vector, and that's added up around the curve. This quantity gives me the flux of the field across C. Now, we're going to calculate that by Green's theorem, but before we calculate it by Green's theorem, we're going to psych it out. What is it? What's the value of that integral? Well, since I'm asking you to do it in your head, there can only be one possible answer. It is 0. Why is that integral 0? Well, because at each point, the field vector, the velocity vector, is perpendicular to the normal vector. Why? The normal vector points perpendicularly to the curve, but the field vector always is tangent to the curve because this curve is a trajectory. It's always supposed to be going in the direction given by that white field vector. You follow? A trajectory means that it's always tangent to the field vector and therefore always perpendicular to the normal vector. So it's equal to, this is 0. 0. Since F dot n is always 0. Everywhere on the curve, F dot n has to be 0. There is no flux of this field across the curve because the field is always in the same direction as the curve, never perpendicular to it, has no component perpendicular to it. Okay, good. Now let's do it the hard way. Let's use Green's theorem. So by Green's theorem says that the flux across C should be equal to the double integral over that region of what? Of the divergence of F. It's like Gauss's theorem in 2 dimensions, this version of it. So divergence of F, that's a function. I double integrate it over the region, and then that's dx dy, or let's say dA, because you might want to do it in polar coordinates. And on the problem set, you certainly will want to do it in polar coordinates. I think, yeah. All right, how much is that? Well, we haven't yet used the hypothesis. All we've done is set up the problem. Now, the hypothesis was that the divergence is never 0 anywhere in D, and therefore the divergence is never 0 anywhere in R. So what I say is the divergence is either greater than 0 everywhere in R, or less than 0 everywhere in R. But it cannot be sometimes 0, positive, and sometimes negative. Why not? In other words, I say it's not possible that the divergence here is 1 and here is -2. That's not possible, because if I drew a line from this point to that, along that line the divergence would start positive and end up negative, and therefore have to be 0 sometime in between. It's because it's a continuous function. It's a continuous function, I'm assuming that, and therefore if it's sometimes positive and sometimes negative, it has to be 0 in between. You can't get continuously from +1 to -2 without passing through 0. Therefore, so the reason for this is since the divergence is never 0 in R, it therefore must always stay positive or always stay negative. Now, if it always stays positive, the conclusion is if it's always positive, then this double integral must be positive. Therefore, the integral is either, this double integral is either greater than 0, that's if the divergence is always positive, or it's less than 0 if the divergence is always negative. But the one thing it cannot be is not 0. Well, so the left-hand side, Green's theorem is supposed to be true. You've got to start with Green's theorem is our bedrock. 1802 would crumble without that, so it must be true. The one way of calculating the left-hand side gives us 0. If we calculate the right-hand side, it's not 0. That's called a contradiction. So where did the contradiction arise from? The contradiction arises from the fact that I suppose that there was a closed trajectory in that region. So the conclusion is there cannot be a closed trajectory in that region because it leads to a contradiction via Green's theorem. Okay, so let me see if I can give you some of the argument for the other. Well, let's at least state the other criterion I wanted to give you. Suppose, for example, we use the this system, x prime equals does this have limit cycles? Does that have limit cycles? Well, let's Bendixson it. Okay, we'll calculate the divergence of the vector field. It's 2x from the top function. The partial with respect to x is 2x. The partial with the second function with respect to y is negative 2y. Well, that certainly could be 0. In fact, this is 0 along the entire line x equals y. Its divergence is 0 here, along that whole line. So the best I could conclude was, I could conclude that there's no limit cycle like this, and there's no limit cycle like this. But there's nothing so far which says that a limit cycle could not cross that, because that would not violate Bendixson's theorem. In other words, any domain which contained part of this line, the divergence would be 0 along that line, and therefore I could conclude nothing. I could have limit cycles which cross that line, as long as they included a piece of that line in them. So the answer is I can't make a conclusion. Well, that's because I'm using the wrong criterion. Let's instead use the critical point criterion. Now, I'm going to state it as it makes a nice positive statement, but nobody ever uses it this way. But nonetheless, let's first state it positively, even though that's not the way to use it. So the positive statement would be, once again, we have our region D, and we have a region of the xy plane, and we have our C, a closed trajectory in it. A closed trajectory of what? Of our system x prime equals of the system. And that's supposed to be in D. For critical point criteria, it says something very simple. If you have that situation, it says that inside that closed trajectory, there must be a critical point somewhere. Ta-da! Okay, it says that the inside C is a critical point. Now, that's not going to help us find, this won't help us with the existence problem. This won't help us find critical point, help us find closed trajectories. You know, we'll take our system and we'll say, oh, it has a critical point here and a critical point there. So does it have a closed trajectory? Well, all I know is the closed trajectory, if it exists, will have to go around one or more of those critical points. But I don't know where. It's not going to go around it like this. It might go around it like this. And my computer search won't find it because it's looking at too small a part of the screen. So it doesn't work that way. It works negatively by contraposition. So the theorem is used in the contrapositive. You know what the contrapositive is? Okay, you can at least learn that. A implies B says the same thing as not B implies not A. These are not two different statements. They are different statements, but they are equivalent to each other. If you prove one, you prove the other. So what would be the contrapositive here is that if you have a closed trajectory, inside is a critical point. So the theorem is used this way. If D has no critical points, if D has no critical points, it has no closed trajectories. Because if it did have a closed trajectory, and therefore it has no limit cycles. Because if it did have a closed trajectory, inside it would be a limit. Inside it would be a critical point, but I said D had no critical points. That enables us to dispose of this system, which Bendixson couldn't handle at all. We can dispose of this system immediately, namely, what is it? It's where are its critical points? Well, where is that 0? X squared plus y squared is 1 plus 1 is never 0. This is positive, or at worst 0, and then I add the 1 to it, and it's not 0 anymore. So this has no zeros, and therefore it doesn't matter that this one has a lot of zeros. It makes no difference. It has no critical points. There has none. Therefore, no limit cycles. Now, I desperately wanted to give you the proof of this. it's clearly impossible in the time remaining. The proof requires a little amount, so I haven't decided what to do about that. It might leak over till Friday's lecture, but instead I'll finish by telling you a story. How's that? And the long side of it was little y prime, which I'm not going to continue on with the letters of the alphabet. I'll prime the earlier ones. So this has a total of 12 parameters in it. But in fact, if you change variables, you can get rid of all the linear terms. So it's really the important part of it is only the quadratic terms in the beginning. So this sort of thing is called a quadratic system. It's the kind of, after you've departed from linear systems, it's the simplest kind there is. And the predator-prey, the robin earthworm example I gave you, is of a typical quadratic system and exhibits typical nonlinear quadratic system behavior. Now, the problem is the following. So A, B, and C, D, and F, and so on, those are just real numbers, parameters, and so I'm allowed to give them any values I want. And the problem that has bothered people since 1880 when it was first proposed is, how many limit cycles can this have? Can a quadratic system have? After 120 years, this problem is totally unsolved, and now the mathematicians of the world who are interested in it cannot even agree with each other on what the right conjecture is. But let me tell you a little bit of its history. There were attempts to solve it in the 20 or 30 years after it was first proposed, through the 1920s and 30s, which all of them seemed to have gaps in them, until finally in around 1950, two Russian mathematicians, one of whom was extremely well known, Petrovsky, a specialist in systems of ordinary differential equations, published a long and difficult, complicated 100-page paper in which they proved that the maximum number is 3. I won't put down their names. Petrovsky and Landis. Okay. The maximum number was 3, and then not many people were able to read the paper, and those who did, there seemed to be gaps in the reasoning at various places, until finally Arnold, who was the greatest Russian, in my opinion, one of the greatest Russian mathematicians, certainly in this field of analysis and differential equations, but in other fields too. He still is great, although he's somewhat older now. Criticized it and said, look, there's a really big gap in this argument, and it really cannot be considered to be proven. So people tried working very hard to patch it up, and without success. And then about 1972 or so, 75 maybe, a Chinese mathematician found a system with 4. A quadratic, wrote down the numbers, that the number A is so much, B is so much. They were absurd numbers like 10 to the minus 6th and 40 billion and so on. Nothing you could plot on a computer screen, but the answer found a system with 4. Nobody after this tried to fill in the gap in the Petrovsky-Landis paper. I was then chairman of the math department, and I had one of my tasks was to, protocol and so on. Anyway, we were trying very hard to attract a Chinese mathematician to our department to become a full professor. He was a really outstanding analyst and specialist in various fields. Anyway, so he came in for a courtesy interview, and we chatted. At the time, I was very much interested in limit cycles, and I had on my desk the Math Society's translation of the Chinese book on limit cycles. a collection of papers by Chinese mathematicians on limit cycle, all on limit cycles. So, you know, after a certain point, he said, oh, he said, I see you're interested in limit cycle problems. So I said, yeah. I said, in particular, I was reading this paper of the mathematician who found 4 limit cycles, and I opened to that system, and I said, the name is, and I read it out loud. I said, do you by any chance know him? And he smiled. He said, yes. He said, very well. That's my mother. Well, bye-bye.